Hey everyone, Mr. Houck here. In today's video, we're going to look at an introduction to vectors. By the end of this lesson, we should be able to understand basic terminology associated with vectors and calculate the magnitude and direction of vectors. Let's go ahead and begin. So what is this idea of a vector? Well, if you scan the QR code or look at the link attached here in the document, you'll be taken to a cute little video that gives a very quick and simple introduction to what a vector is. But essentially, a vector is a directed line segment that has both a magnitude and a direction. Now, these vector quantities, some examples of them are force and velocity from physics. Since they have both a magnitude and a direction, we cannot simply characterize them using a single real number. Now, one of the challenges that we're going to face with vectors is all the new notation and terminology that we're going to be using throughout this unit. So here are the notations we're going to concern ourselves with when it comes to vectors. We can represent a vector as a bolded lowercase letter, usually v. We can represent a vector as a lowercase letter with an arrow above it, or a ray. Notice, for example, here, AB, this would represent a starting point and an ending point, again, with an arrow above it to represent a ray. Or we can also represent a vector as an ordered pair in what I call pointy brackets. Notice these are pointy, these are not parentheses like we would normally see an ordered pair in. So this is another way that we can represent a vector. So let's consider the vector v to the right over here. Vectors have initial starting points and terminal ending points. So in this example, the initial point is where the vector starts, in this case, point P. The terminal point is where the vector ends, in this case, point Q, so we call this vector PQ. Initial point first, terminal point last, P then Q. Now we say that a vector is a standard vector when its initial point is at the origin. Every single vector in a plane is equivalent to some standard vector in that plane. So given the plane here to the right where we have three vectors, one in green, red, and blue, we want to circle the vector to the right that is a standard vector. Well, again, let's remind ourselves of the definition. A standard vector is a vector whose initial point is at the origin. The only vector over here whose initial point is at the origin is this vector in red. Let's keep the colors consistent. I'll go with red right there. Okay, so that vector in red is a standard vector. Its initial point is at the origin. So as we alluded to earlier, vectors are these quantities that have both magnitudes and direction. The magnitude of a vector is its length. And if we have 2 points for a vector, or if we know the initial point and the terminal point, then we can use the distance formula, which is provided right here. And that will give us the magnitude or the length of that vector. Now, just like where we had those different notations right here to represent a vector quantity, we also have different notations to represent the magnitude of a vector. Now we have the name of the vector. So again, remember that vectors are represented by lowercase letters, lowercase bolded letters. So if I have that letter in what looks like absolute value signs, absolute value brackets, that would represent the magnitude. We have the letter in what looks like double absolute value brackets, that represents the magnitude. Or if we just simply have that lowercase letter italicized, that could also represent the magnitude. Now, most of the time, we're going to go with this option right here because it's the most unique, easiest to tell. So this one right here is going to be the most common with what looks like double absolute value brackets. Okay, so this is what we'll use the vast majority of the time. Just be aware of your other notations here. Okay. So the direction of a vector, the other component to a vector, is determined by finding the slope. I'm going to go ahead and highlight that. Finding the slope of the segment between its initial point and its terminal points using the slope formula, y2 minus y1 divided by x2 minus x1. Remember, we're talking about initial and terminal points. So the initial point would be x1, y1. The terminal point would be x2, y2. We can also sometimes represent the direction of a vector using our compass directions like north, south, east, west, northeast, northwest, southeast, southwest, north, northeast, so on and so forth. Now, one of the interesting definitions we need to establish is displacement. And if you've taken physics or physical science before, you might have been introduced to displacement already. But displacement is a vector quantity that refers to how far out of place an object is relative to the object's initial position. Displacement is different from distance. A lot of students tend to confuse displacement and distance with each other. And here's a good example to help establish the difference. So let's say that in this example right here, each square is going to represent 1 meter in length. So starting at point A, here's our initial position. A person walks 3 meters north. We can see that because there's 1, 2, 3 square lengths. 4 meters east, 3 meters south, and then 4 meters west. Notice that the starting position is also the ending position. So even though this person traveled a total distance of 14 meters, because 3 plus 4 plus 3 plus 4, that would give us 14 meters. The distance is 14 meters, but the displacement is 0 meters. And that's because displacement is a vector quantity and direction must be considered. So the north direction, the 3 meters north, canceled with the 3 meters south, and the 4 meters east canceled with the 4 meters west. So the displacement was 0, but the total distance traveled was 14 meters. Let's try another example of displacement here. So Catherine is hiking from camp and travels 3 miles east and 2 miles north. We want to find Catherine's displacement. Okay, well, on our little image here, again, here's the starting point, the camp. Catherine travels 3 miles east, and then Catherine's going to travel 2 miles north. So the displacement is the distance from the beginning, the camp, to the end. And again, displacement is a vector quantity, so we not only need to include the magnitude or the length, but the direction. Well, notice that we can find this length pretty easily using Pythagorean's theorem, because the 3 miles east and 2 miles north creates a right triangle. So I'm going to go ahead and call the displacement x. And x, or the displacement x, is going to be equal to the length of x. So to find x, let's go ahead and use Pythagorean's theorem. So 2 squared, one of the legs, plus 3 squared, the other leg, is going to equal the length x squared, or it's going to equal x squared. 2 squared is 4, 3 squared is 9, 4 plus 9 is 13. And we know that we can take the square root of both sides to find the length of x. So x is equal to the square root of 13. However, this is an application problem. Square root of 13 doesn't make too much sense to us right now. So let's go ahead and approximate the square root of 13. This would give us approximately 3.61 miles. Okay, 3.61 miles. But remember that this is a vector quantity. So yes, it's 3.61 miles, but the direction would be northeast because we traveled both east and then north. Okay, 3.61 miles northeast. So now let's talk about equivalent vectors. Two vectors that have the same magnitude and direction are said to be equivalent. Equivalent vectors can essentially be thought of as congruent segments on parallel lines, same direction and length. And here are some examples to the right. Each of these examples to the right over here on this coordinate plane can be thought of as equivalent vectors. Again, notice they have the same magnitude or the same length, and they're running in the same direction. A zero vector is any vector of magnitude equal to 0. Now, while zero vectors must have a magnitude of 0, they can be moving in any direction. In component form, and we'll talk about component form here very soon, a zero vector is represented as 0, 0, or 0, 0, 0 in three-dimensional space. And again, we'll talk about component form here in just a moment. But let's think about if we can understand what these zero vectors, what an example could be in a real-life scenario. One example that I can think of is think about tug of war. Let's say that you have two evenly matched teams in a tug of war contest, and both teams are pulling in opposite directions, equal and opposite forces, that would be considered an example of a zero vector. Okay, zero magnitude, but it still has direction. So I'm going to go ahead and write that down here as an evenly matched tug-of-war contest. That'd be an example of a zero vector. Okay. Try to think of an example of a tug-of-war, or not a tug-of-war contest, but try to think of an example of a zero vector in real life. They're a little bit tricky to think of sometimes. So that's what a zero vector is, but a unit vector is any vector with a magnitude of 1. And again, remember magnitude we represent with these little double bars here. So the magnitude of v would be equal to 1 if the vector was named v. Now, I told you we would talk about this component form just a moment ago, and we call the vectors I, j, and k. These are the unit vectors along the different axes. So I is the unit vector for the positive x-axis, j is the unit vector for the positive y-axis, and k is the unit vector along the positive z-axis. And we know that in an ordered pair, the x-axis comes first, so I would be 1, 0, because it's going along the x-axis. There's not along the y or z-axis. I in 3 dimensions would be 1, 0, 0. Again, 0 for the y, 0 for the z, but 1 for the x. J is for the positive y-axis, so we'd have 0 in the x direction, but 1 in the y direction, or in 3-dimensional space, 0 in the x direction, 1 in the y direction, 0 in the z direction. And k, so in the case that there are 3 dimensions, you would have a k value, and k would be the unit vector for the k direction, would be 1. So 0 in the x direction, 0 in the y direction, 1 in the k direction, or in the z direction rather. Okay, so essentially I represents the x coordinate, j represents the y coordinate, and k represents the z coordinate. And again, these are unit vectors for the individual x, y, and z coordinates. If we have a vector written component form right here, and we have, this is the x component, this is the y component, and we know what those components are, then the magnitude of a vector written in component form like that would be the sum of the squares of the components. So, here's the x component squared, here's the y component squared, and then we would take the square root of their sums. Likewise for vector in 3-dimensional space, let's say that we have a 3-dimensional vector. Here's our x component, y component, z component, or I, j, k. Then the magnitude of that vector, we would take all 3 of those components, square them, add them together, and take their square root. Now to find the direction of a 2-dimensional vector, we're going to leave out 3-dimensional vectors. The direction of a 2-dimensional vector, let's say we have the x component and the y component, we would find the direction by basically calculating the slope essentially. We would take the y direction, or the y component, and divide it by the x component, and that would give us the direction of that vector. Again, that's the y component divided by the x component. So let's try a little bit of mixed practice here. In the first 2 examples, we want to take the given vector and write it as a linear combination of the standard unit vectors. Remember, the standard unit vectors are I, j, and k. So here in our first example, we have the vector -3, 5. Again, we know it's a vector because we have these little pointy brackets here. -3 is the basically the x coordinate, or the x component, and 5 is the kind of like the y coordinate, or the y component here. So if I wanted to write these as a linear combination of standard unit vectors, remember that I is the unit vector in the x direction. So -3 I plus, and then we can see that 5 here is in the y direction. That's the j the j vector. So this would be plus 5j. If we look over here to the next example, again, we want to take the given vector, right, as a linear combination of standard unit vectors. So this would be 4 is in i's position. This would be 4i minus 2j plus 9k. Again, this is like the x component, the y component, the z component. Now let's do that same process, but given the linear combination of standard unit vectors, let's write the vectors in component form. So we have negative 3i plus 1j minus 2k. This would be negative 3, 1, negative 2. And we're getting that by looking at the coefficients. Coefficient negative 3 for I, that's the x component. Coefficient of j is 1, that's the y component. Coefficient of k is negative 2, that's the z component. Let's try this one. We have the given standard unit vector 4k. Notice that we don't have an I or a j, so this is almost like saying 0i plus 0j plus 4k. So the x component would be 0, the y component would be 0, but the z component would be 4. Okay, so that's the vector 0, 0, 4. In our next problem, given that the vector v is 7, negative 12, find the magnitude of v and the direction of v. Again, remember magnitude is the length. So we have our x component and our y component, and if we want to find the magnitude of this vector or the length of this vector, well, we already know the x and y components here, so to find the magnitude of v, let's use a different color here, we'll go with red. To find the magnitude of v, we would simply take the square root of the sum of those components squared. So the x component squared, 7 squared, plus the y component squared, negative 12 squared. Notice that the y component is negative, so I have these parentheses. Pretty important, especially when you plug it into the calculator here. So we have 7 squared, which is 49. Negative 12 squared, so negative 12 times negative 12, that's plus 144. And when we go to calculate this, 144 plus 49, that's going to give us a square root of 193. And square root of 193 cannot be simplified any further, so the magnitude of v is the square root of 193. Okay. Now let's find the direction of v. So the direction of v, when written in component form, is the y component divided by the x component. So the direction would be, and I'm going to write direction equals again, it's going to be the y component divided by the x component, so that'd be negative 12 over 7. That fraction cannot reduce, so there's our direction. And our last example here, you and your friends are at a ski weekend trip for your school. While skiing, you go down a rather steep hill. The motion from the top of the hill going down can be represented by a vector. Counting the top of the hill as the origin, you ski down a slope and measure how far your x and y positions have changed. As it turns out, you can represent this displacement with a vector 12, negative 256. What is the slope of the vector, and what does the slope mean in context? Well, we already know that the slope of the vector is representing the direction, so slope equals direction. And we know the direction is going to be the y position, or the y component, negative 256, divided by the x component, which is 12. Well, negative 256 divided by negative 12. Let's go ahead and approximate that. This isn't an application problem, so we want to approximate it as a decimal so that it makes a little more sense to us. This would be about negative 21.33. So this is the direction, negative 21.33 here, or the slope. Now, what does that actually mean in context? Well, remember, we're talking about going down a steep hill while skiing. So what this means, remember, if we're representing this as a slope, this is like negative 21.33 over 1, where the negative 21.33 is like the y component, and the 1 is like the x component. So what this is really representing is that for every 1 foot, so for every 1 foot, the hill changes in the x direction. Okay, for every 1 foot, the hill changes in the x direction. It goes down 21.33 feet in the y direction. We know it's going down because we have a negative direction. So for every 1 foot the hill changes in the x direction, it goes down 21.33 feet in the y direction. Okay, and that's pretty easy to think of. Again, in this example, we can think of the top of this hill as the origin, and we can see that as we are going to the right, for every, we'll call that 1 foot in the x direction, then it's going 21.33 feet in the y direction. And that's one way that we can kind of quantify that vector there.